Hello programmers! Today we're going to talk about binary search trees. Before we get into the binary search trees, let's do a little bit of a review about linked lists, where you have a piece of data and then a pointer to the next item in your linked list. And here I've got a linked list of integers. If you want to find something in the linked list, how long does that take? Well, we have something called a big O notation. That is a way to talk about the relative amount of time it takes to do an operation based on the number of items or the n time. So in this example, if you want to search and try to say, is 10 in the linked list, you start at the beginning. It's not 2, you follow the pointer. It's not 5, you follow the pointer. It's not 8, you follow the pointer, and 10 is smaller than 12. So if this is a sorted linked list of integers and you get to 12 without seeing 10, then 10 wasn't there. The worst case scenario, you search everything in this list. It's a big O of n time. For searching, for inserting in the right position, deleting is fast if you know where it is you want to delete something from, but finding the position of the item you want to delete is big O of n. And the big O of n time isn't the best that we can do. Another data structure that involves nodes and pointers is something called a tree. A tree, it has data and then pointers to the children in the tree. What is a binary tree? Well, a binary tree is a tree where you have the data and pointers to the children, and with binary, it means you can have at most 2 children. You could have no children, like 5 in this binary search tree. You could have 1 child, like 6, or you could have 2 children, like 4. What also makes the binary trees special, or the binary search trees special, is that binary search trees have a property where all of the nodes to the left are going to be smaller and all the nodes to the right are going to be greater. So if I look at 4, everything on the left side of the tree, all its children and grandchildren, are all smaller than 4. Everything on the right side is greater than 4. And each of the individual nodes in this tree, like 2, everything to the left is smaller than 2, everything to the right is greater than 3. The really cool thing about binary search trees is they have a big O of log n time for insertion, deletion, and searching in the best case scenario. And the best case is if you've got a balanced tree. Binary search trees are node-based. I want each node in my example to hold a high score, a username, and then a pointer to the left and the right child, and if they don't have children, we'll use null or a 0 in place of those children. So in C, it's going to look something like this. I'm going to create a structure for each of the nodes in the binary search tree that has a high score, an array of char for the username, and then pointers to the next thing on the left or the right. So the very first time you're adding something to your binary search tree, your root node is going to be pointing at nothing. There's nothing in the tree yet. So we'll need to ask the user, what's the name of the person with the high score? What's the number you want to add for the high score? We'll dynamically allocate enough memory for that binary search tree node with malloc, and then we'll go ahead and make that our root. So I'm going to start with a few includes. I need standard IO because I'm doing printf and scanf. I need standard lib for malloc, and I need the string header for later on. I'm going to do comparisons between different usernames to see if the node should go on the right or the left side of the tree. And instead of comparing integers like a lot of the examples, I wanted to use an example where you're comparing strings or arrays of characters. So I'll go ahead and start with my struct. The first thing we need to do is create a function to add things to our binary search tree. I'm going to have an add function where it takes 2 input arguments. One is the current root and the other is the node that you want to add to your binary search tree. My return type is also a pointer to the root of the binary search tree. Special case, if the root is null, if it's an empty binary search tree, then you want to put that new node becomes the root. So we'll say root is equal to node. And we want to return the root from this function. This is the one case where the root has changed. It used to be pointing to null. Now it's going to point to your new node that you've malloced. The next two cases we're going to look at is when you're comparing the username of your root. It's not null because we made it past the first if. If you're comparing that username with the node's username, then it could be that alphabetically the username you're trying to add comes after the root's username. That's the one I'm doing right now. In that case, you need to go to the right side of the tree. So if you're looking at that right child pointer and it is null, if it's empty, then it's pretty clear you're just going to update the pointer for that right child of the root to point to your new node. If it's not null, then we're going to do something different. If it's not null, then I'm going to use recursion. Recursive function is a function that calls itself. So I'm going to actually call the add function, only instead of the root that I have right now, I'm going to pass in the right child and that node and see where on that right side of the tree can I add this node. All right, we've also got the case that's very similar where the username for the root and the username that we want to add, and the username goes to the left side of the tree. So in that case, string compare is going to return something that is greater than 0. It took me a while to remember to fix that in the code, but I will be changing that soon. So we've got our left child. If it's null, we just update the pointer. And if it's not null, we'll do the same thing we did where we're going to do recursion and use the pointer to the left child and treat that as the root for our next call to add. In binary search trees, you don't often have two of the search terms, whether they're usernames in this case or integers in other cases. Usually they're not identical. I'm going to put an error message if somebody tries to add a username that's already in the tree. So now to be able to see if this is working or not, we're going to need to make a print function to be able to print what is actually in our binary search tree. This function is going to take a pointer to our root. If it's null, there's nothing to print. If it's not null, I'm going to use recursion again and print everything on the left subtree. And then I'll print the node I'm currently on. And then I've got recursion again. I'll print everything that's on the right subtree. Recursion is really useful in this program. Now to test this out, we need a main function, and in main I'm going to create some variables. One variable is obviously going to be the root, which starts out as null. Another variable I'm going to have is going to be the new node that we want to add if somebody says they want to add. And another is the operation. Do you want to add to the binary search tree, update, delete, etc., or just print out what's in the binary search tree? This is going to probably spread into 2 videos, but for now we've got our add and we've got our printing of the binary search tree, and I'll put in options for update and delete, but those are probably going to be in the next video. So what should we do if somebody says they want to add to the binary search tree? Well, I'm going to dynamically allocate some memory that is big enough to have a binary search tree object. So a high score, a username, and then our pointers to the left child and the right child. we'll have the left child and the right child start out as null. We'll update the pointers in the add function if we need to. And then we'll call that add function and make sure that you don't forget to save the result of calling add, because the first time you call it, the root is going to change. It's going to be that new node. So this is a common mistake for students to forget this line. And now if the user says that they want to print the binary search tree, we'll call our print tree function. That's it. In the real world, we're going to also want to implement the option 2 and option 3 and also release any of that memory that's allocated, but I'm going to add that to my next video. Let me just finish up my do while condition. I told the user that if they typed in 5, it would exit. I'm going to say if they typed anything less than 5, we're going to keep going through the while loop. Anything else, we're going to exit. Let me try to test it. Looks like I've got one extra curly brace here. Go ahead and run it. We'll first try to add a user to our binary search tree. We'll add Bob with a high score of 5. Now we'll add Anne with a score of 5. That should go on the left side of the binary search tree because Anne is less than Bob. And if we add somebody else that has a name greater than Bob, it'll go to the right side of the binary search tree. I've got a few review questions for you. But what happens to your binary tree if you're adding numbers 1, 2, then 3, then 4, then 5? Well, 1 starts out as your root node, and then the next thing you add is bigger than 1, so it goes to the right side. The next thing's bigger than 2, so it goes to the right side, and you end up with just a linked list, and you're not going to achieve that big O of log n time. So what you need to achieve that is a balanced tree. So let's look at a few examples. Would you say this is a binary tree? And go ahead and pause the video if you want to think about it. Each node has at most 2 children, so it is a binary tree, but in a binary search tree, everything to the left is going to be less and everything to the right is going to be greater. And this number 15, that's a child of 5, that's a problem. That never would have made it to this side of the tree because it is not less than 10, so it wouldn't have gone to the left subtree. So this is not a valid binary search tree, but it is a valid binary tree. What about this one? Do you think this is a binary search tree? And the answer is no. This is not a binary search tree. It's not even a binary tree because we've got 3 children of 20, and in binary trees you can only have at most 2 children. Is this a binary search tree? Well, you might think binary is 2, and you don't have to have every node having 2 children. Like, it's okay for 5 to just have 1 child. This is still a binary search tree because it's got the property that each node has at most 2 children, and also every node to the left is going to be smaller and every node to the right is going to be larger. So this is a binary search tree.